In this video, we're going to learn how to simplify radical expressions. We're going to see cube roots and square roots that are not perfect, as in like the square root of 36 was just 6. Now we're going to see things like square root of 12, square root of 98, and we need to know how to simplify those. So we have a process that I've outlined over here to the right. We're going to prime factor the number. For a square root, we're going to look for pairs, cube root, 3 of a kind, fourth root, 4 of a kind, and so forth. And then we're going to take out those pairs or 3 of a kind. When I say take out, we're going to take them outside of the radical. This is a very easy lesson. Let's look at this first example, the square root of 12. So if we prime factor 12, remember you can do it through little trees if you'd like that. And so this equals 2 times 2 times 3. So what we have, 2 times 2 is 4. That's a perfect square. And so we should know that the square root of 4 is just 2. So that's what I mean look for pairs, because those would be a perfect square. And so those can come outside of the radical. And so we could rewrite that as 2 times the square root of 3. Let me give you an alternative way to look at that. Some books do it this way. And so they might look at it as the square root of 4 times the square root of 3. And you could look at it separating those two radicals, and then of course the square root of 4 is 2. So either way, we still end up with the answer of 2 times the square root of 3. I prefer the prime factoring method because as the numbers get bigger and we have cube roots and fourth roots, I find it easier. Alright, so I'm going to look at 98. Now I know since that's an even number, it's divisible by 2. So I say 2 goes into 98 49 times. And then I know 49 is 7 times 7. So I can look at this as 7 times 7 times 2. I have that perfect square, or that pair, that comes outside of the radical, so that's 7 times the square root of 2. Again, if you can do some prime factorization, which is just division, this is a very easy lesson. Alright, notice these two problems. We have a square root and we have a cube root. Well, let's do that square root one more time. 150, I know it ends with a 0, so I know that's divisible by 10. I know that's 10 times 15, that's 2 times 5, and that's 5 times 3. So I have a pair of 5s. So that's going to come outside of the radical. And then what do I have left? I have a 2 and a 3. And we need to multiply those together and get 6. So the square root of 150 is 5 times the square root of 6, because again, I had that perfect square in there. That's really 25, and the square root of 25 is just 5. Just don't forget, when you have other stuff that aren't paired up, you need to multiply all those back together. Now let's look at that cube root. Well, a cube root, we're looking for 3 of a kind. But my process is the same. I'm still going to do some prime factorization. So I think of this as 8 times 5. And I know 8 is 2 times 2 times 2. We've done that a lot in previous videos. And so because I'm looking for a perfect cube root, I have a 3 of a kind. So that's going to come outside of the radical. The 5 stays inside, and what you want to make sure you write is the cube root. This little number is very important. If you leave that out, then your answer is 2 times the square root of 5. And that's wrong. So that little bitty number right there, if you leave it out, that is going to cost you some points. You see we have 2 more cube roots, and again we're looking for 3 of a kind because those would be perfect cubes. So 54, I know that on my times table as 6 times 9. 6 can be broken apart as 2 times 3, and 9 as 3 times 3. So again, since I'm looking for a cube root, I'm looking for 3 of a kind, and so that comes outside of the radical, and then the 2 stays inside. And again, don't forget that little index to make sure we're talking about a cube root. Right, one more. 240, the numbers are getting a little bit bigger. I know that's 10 times 24 because that ends in 0. Then 10 is 2 times 5, and 24, well, It's a lot of things. The first thing that came to my mind was 6 times 4. I'm going to break that apart. I'm going to break that apart. Now that's a lot of numbers, so I'm just going to write this all out so I don't forget anything. I've got a 2, a 5, a 2, a 3. Oh, and I've made a mistake. That should be another 2, right? 4 is 2 times 2. So let me get this again. 2 times 5, 2 times 3, and 2 times 2. Do we have 3 of a kind? Let's see. I've got those two 2's with that 2. That would be 3 of a kind. So the 2 comes outside, then I have my cube root sign, and what do I have left that I didn't circle? A 2, a 5, and a 3. A 2, a 5, and a 3. Multiplying all that together, 2 times 5 is 10, times 3 is 30. So you can see how easy it is to make a little mistake. Just check your work. So now we see, fourth roots, but the process is the same, right? So 48, I think about that on my times tables. There's lots of things that multiply to get 48, but the first thing that came to my mind was 6 times 8. I'm going to break apart 6. I'm going to break apart 8, and I already know that that's 3 2's. And since this is the fourth root, I'm looking for 4 of a kind. And I have 4 2's. So the 2 comes out, the fourth root radical is there, and that 3 stays inside that radical. Now the fourth root of 240, I just did that problem. Or did I? I just did the cube root. So the fourth root, we would still break that apart. We just got through doing that. So let's write that down again. I think I had written it down initially like that. 2 times 5 is the 10, and 2 times 3 is the 6, and 2 times 2 is the 4. It doesn't really matter how you got there, but that's the prime factorization. And that's why I like this method, because it works for any kind of radical. So I'm looking for not 3 of a kind, but 4 of a kind. So I've got those two 2's, that 2, and that 2. 1, 2, 3, 4 2's. So the 2 can come outside of the radical, which is a fourth root, and then I've got those two things left over, which is 5 times 3 is 15. Now if you go back at that and compare that to the answer of the cube root of 240, very different. And so that's why that little bitty index makes a difference. Now that's pretty easy. Those are with numbers. The next thing we're going to look at are the same thing except with variables. So you see we have the same problem, but not quite. One's a square root, one's a cube root. So what are we going to do? Square root, we look for pairs. So one method is to actually write what x cubed means. What does x squared mean? And since we're looking for a square root, I'm looking for 2 of a kind. So I have 2 x's and 2 y's. So both of those come outside of the radical, and then what I didn't circle stays inside. Very simple process. Is that going to be the same answer as the next one? No, because I'm looking for a cube root. So just like before, I have 3 x's and 2 y's, but I'm looking for 3 of a kind. So the x comes out. Oop, I left out my little index, and I've been fussing at y'all, so I need to put that little 3. And so I have the cube root of y times y, which is y squared. Now, my handwriting is really bad, so I'm going to write that one more time. So that's x cube root of y squared. Sometimes that little index there has a tendency to get too close to that, and it looks like an exponent. So try to be a little bit neater than me. What happens when those exponents get a little bit larger? Is there a better process than writing all those out and circling the little pairs? I think so. So let's look at that. These exponents aren't that large, and we're looking for the fourth root. But I want you to be reminded of something. What is that fourth root as an exponent? If you remember, the square root of, say, x is the same as x to the half power. The cube root is the 1/3 power, fourth root is the 1/4 power, and so forth. So I could rewrite this as x to the fourth, y to the fifth, z to the 6th, all raised to the 1/4 power. And then, using my rules of exponents, I actually could multiply those together, and I'd have x 4 over 4, y 5 over 4, and z 6 over 4. Now let's reduce. 4 over 4 is to the first power. But what about this? This is really dividing. How many times does 4 go into 5? Well, it goes in one time with 1 left over. So I'm going to write it like that, 1y and 1y. What about here? 4 goes into 6 one time with 2 left over. Now, why am I writing it like that? Just give me a minute. So this is going to be, that's the answer. Now, why is that the answer? Well, if we go back to what this means, those were 4 x's, 5 y's, and 6 z's, and I want the 4th root. So I'm grouping them, which is really a division. And notice I had 1 x, 1 group of y, 1 group of z's, and what did I have left over? I had 1 y, which is here, and 2 z's that are there. So what you can really do here, if you wanted to not write it all out, you can divide the exponents. Let's look at one last example to try to convince you that why dividing the exponent would be a little bit easier. Okay, so here I have the 4th root, and look at those exponents. They're huge. I do not want to write out 100 x's. Okay, so again, I'm going to take the exponent and divide it by the root. And say, all right, that goes in there 25 times with none left over. 52, which is the next exponent, divided by 4, which is the root. That goes in there 13 times with none left over. But 31, let's see, 4 goes into 31, I think, 7 times. 7 times 4 is 28, with a remainder of 3. So the remainder is what stays inside the radical. Those would be the exponents. So I have x to the 25th, y to the 13th, z to the 7th, and then the 4th root of, what's the only thing I had a remainder of, were the z's, z cubed. Just give it a try.